This is exercise 4C, continued, question 18. A body falling through air experiences acceleration at -40 e to the -2t meters per second, and upwards is positive initially, so when time equals 0, the ball is thrown upwards with speed 15 meters per second, so the velocity is positive 15 meters per second. And it says taking the origin at the point where it's thrown, find the functions of v and x and find when the body is stationary. So to find v, you would need to integrate -40e to the -2t with respect to t. So that would be -40 times 1 over -2e to the 2t plus c. Sorry, that's a -2 there. And when t equals 0, v is 15, therefore we've got that 15 is equal to -40 over -2e to the 0 plus c. So therefore 15 equals, that's 20, e to the 0 is 1, 20 plus c, which means that c is -5. And so therefore v is equal to, what have we got? We've got 20, -40 times -1 on 2 is 20 e to the -2t minus 5. Now to find x equals the integral of v dt, so it's the integral of 20e to the -2t minus 5 dt. Integrating that, we get 20 times -1 on 2e to the -2t minus 5t plus c, which is -10 e to the -2t minus 5t plus c. Now, when initially it says taking the origin at the point where it's thrown. So when t is 0, we know that x is 0. Therefore, 0 equals -10 e to the 0 minus 0, that's the 5t, plus c. Therefore, c must equal negative, so this is -10 times 1, and so therefore c equals +10. Therefore, x equals -10 e to the -2t minus 5t plus 10. So when is the body stationary? The body is stationary when the velocity equals 0, which is 20 e to the -2t minus 5 equals 0. So e to the -2t will be equal to 5 over 20, which is a quarter. E to the -2t equals 5 over 20, which is a quarter. Taking logs of both sides, we've got that -2t equals ln of a quarter, and t equals ln 1/4 divided by -2, which is, now ln a quarter is ln 1 minus ln 2, minus ln 4 over -2, sorry. Now ln 1 is 0, so it's negative ln 2, but ln 4 is ln 2 squared, so it will be 0 minus 2 ln 2 over -2, and the -2's cancel, and we get that the time is ln 2. Okay, so it's at time ln 2 seconds. Okay, so do not, this is ln 1 minus ln 4, and ln 4 is ln 2 squared, which is 2 ln 2, and then you can cancel. So you really have to find the exact form and then simplify it as well. Okay, that's part A. Part B is, I'll just make this a bit, so you can see it a bit better. Part B is to find the maximum height and the acceleration then. So maximum height, you want to maximize the height. So maximum height is when dx dt, which is 0. That is when v equals 0. That is when t is equal to ln2. So the maximum height will occur when t is ln2, and substituting that into the x equation for x, we get x equals negative 10 e to the negative 2 ln2 minus 5 ln2 plus c, sorry, not plus c, plus 10, which is negative 10 e to the negative, now 2 ln2 is ln2 squared, which is ln4, minus 5 ln2 plus 10. Now, this is negative 10 times e to the negative 1, or e to the ln, actually, would be e ln 4 to the power of negative 1, because e to the power of negative ln 4 times negative 1 is negative ln 4, that works, minus 5 ln 2 plus 10. Now we know that e ln 4 is 4, so that's negative 10. This is over e ln 4. So to the power of negative 1 means over e ln 4, which is just over 4, minus 5 ln 2 plus 10. Now negative 10 on 4 is negative 2.5. Negative 2.5 plus 10 is 7.5, minus 5 ln 2. So that's the maximum height, and the units are in meters. And the acceleration then, so when a equals, no, not when a equals, when t equals ln 2, so when t equals ln 2, we have to see what the acceleration is. Acceleration is negative 40 e to the negative 2 ln 2, because the equation for acceleration is acceleration equals negative 40 e to the negative 2 t. So just what we were doing before, that's negative 40 e to the negative, again, ln 4, because 2 ln 2 is ln 2 squared. So we'll just do what we did before, and that is negative 40 times e ln 4 to the power of negative 1, which is negative 40 over e ln 4, which is negative 40 over 4, which is negative 10 meters per second. Now, this makes sense, because if a particle is being thrown in the air upwards, the force acting on it is, the acceleration is due to gravity, which is approximately 10 meters per second, and it's negative because it's acting downwards. Acceleration is 10 meters per second downwards. Okay, and now for part C, is to describe the velocity of the body as t approaches infinity. So our equations are, I just have to get those equations. T gets very large, or t approaches infinity, x will approach, now negative 10 e to the negative 2t, actually, you can just do it on your calculator if you want, but that will approach, I think it will approach 0, because negative 10 e to the negative 2t looks like this. Yeah, because e, for example, 10 e to the negative 2t looks like that. That would be negative 10 e to the negative 2t. So as t approaches infinity, that bit approaches 0. Actually, it's not going to approach, the whole thing won't approach 0. So as t approaches infinity, negative 10e to the negative 2t approaches 0. We can write that. And the negative 5t approaches infinity. So therefore, as t approaches infinity, this bit will approach 0. This bit is approaching infinity as well, so x would approach infinity. But actually the question doesn't ask that, sorry about that. It says to describe the velocity as t approaches infinity, so we need to do it over here. So as t approaches infinity, the 20e to the negative 2t, similar graph as that, will look like this. That approaches 0, therefore velocity will approach negative 0 minus 5, which is negative 5 meters per second. So therefore, as t approaches infinity, the velocity approaches negative 5 meters per second. So velocity approaches 5 meters per second, but in the downwards direction, downwards. Okay, now for question 19. Okay, it says that a particle is subject to an acceleration of negative 2 cos t meters per second. Initially, it is at x equals 2, so when t is 0, when t is 0, x equals 2, velocity equals 1 meter per second. And it also says that the travel time, it travels for 2 pi seconds. Now the question is, part A, to find the functions of v and x. So that's acceleration. V will be the integral of the acceleration. So integral of negative 2 cos t dt, cos t dt, which is negative 2 times, if you integrate cos, you just get a straight sine plus c. Now, so it's negative 2 sine t plus c. So we also know that when time is 0, that the velocity is 1. So therefore 1 equals negative 2 times sine 0 plus c. So therefore c is, sorry, not 0, c is 1, because sine 0 is 0. So therefore v equals negative 2 sine t plus 1. Now that's the function for velocity. We may as well do the function for x. X equals the integral of v, which is negative 2 sine t plus 1 dt. Integrating sine, you get negative cos, so you'll get negative 2 times negative cos t plus c. So therefore x is positive 2 cos t plus c. Substituting when t is 0, x is 2. And we get that 2 equals 2 times cos of 0, which is 1, plus 0 plus c. So therefore c equals 0 in this case, because cos 0 is 1. So we get that c is basically 2 minus 2, which is 0. So therefore x is 2 cos t plus t. Okay, part B, when is the acceleration positive? Now the best thing to do, I would just sketch this curve. It's just so easy to do it this way. And there's your acceleration, and here's your time. We're sketching the curve for acceleration. Now the curve is negative 2 cos t, and we know we've got it travels for 2 pi seconds, so the period's 2 pi, and we can see that because the period is 2 pi over 1. Sorry, the length of the graph will be 2 pi, but the period's also 2 pi. So it's a negative cos curve with an amplitude of 2. So negative cos curve looks like this. Amplitude of 2, travels for 2 pi seconds, so therefore this is pi, and this is pi and 2, and that's 3 pi and 2. And the question is, when is the acceleration positive? So when it's between, so the acceleration is greater than 0 for t lying between pi on 2, and 3 pi on 2. It's just a bit above the graph here. So drawing the graph really helps answer that question. Part C, when and where is the particle stationary and when is it moving backwards? Again, I'd be doing the sketch for X. That's a bit harder to do because X equals 2 cos t plus t. So when and where is the particle stationary is going to be a bit harder to do. Because that's displacement. We need velocity. So when and where is it stationary? It's asking us, sorry about that, when v equals 0. So when does v equal 0 and where is the particle when v is 0? So let's put v equals 0 here. So we've got negative 2 sine t plus 1 is 0. Therefore, sine t is negative 1 over negative 2, which is a half. And it's quite easy to solve. We know sine 30 is a half, or pi on sine. So therefore, t is pi on 6. Now, I'm going to draw the velocity curve over here so that it makes sense for us. So we know v equals negative 2 sine t plus 1. So it's a negative sine curve shifted up 1 unit. So instead of being down here, actually I'm going to draw it double amplitude. So this will be, I'm going to go like this. So this is 1. So normally the sine curve goes from this one will go from 2 to negative 2 because we're trying to sketch negative 2 sine t plus 1. So the normal 2 sine t goes from 2 to negative 2. It's got an amplitude of 2, but this is the negative 1. So it would have been down here. And then we're shifting it up 1. So if we add 1 to the 2, we get 3. And if we add 1 to the negative 1, to the negative 2, sorry, we get negative 1. So the curve is now going to go from, instead of from negative 2 to 2, so instead of negative 2 to 2, which it would have gone from, add 1 to each of those, it's going to go from negative 1 to 3. Centre of the motion here will be 1. It only goes for 2 pi seconds. This point is pi. Here is pi on 2, and up there's 3 pi on 2. So the question is, when is the velocity 0? Well, I can see it's 0 there and there. So in other words, I do need 2 solutions here. I do have quadrants 1 and 2. So sine is positive in quadrants 1 and 2. So I'll just draw my little thing here. Sine of 30, which is pi on 6. And pi on 6. Quadrant 1 is pi on 6 and quadrant 2 is 5 pi on 6. So therefore, the velocity is 0. So velocity is 0, or particle stationary, in other words, when t equals pi on 6 and 5 pi on 6 seconds. Now, where is the particle? So I'm going to substitute. We've got x equals 2 cos t plus t. So when t equals pi on 6, x is 2 cos pi on 6 plus t. Now the cos of pi on 6, that's cos 30, is root 3 on 2. So it's 2 root 3 on 2 plus pi on 6, which is root 3 plus pi on 6. So that's where it is. And when t equals 5 pi on 6, x equals 2 cos 5 pi on 6 plus 5 pi on 6. Now that's the cos of 150, which is negative cos 30, which is negative root 3 on 2. So it's negative root 3 plus 5 pi on 6. Now that's the position of the particle. And it is better to write that as 5 pi on 6 minus root 3 because you may not see that negative at the front. So that's the position. I think it's meters. By the looks of things, it is. So that is when and where is the particle stationary. We've got the when and we've got the where it is. And when is it moving backwards? So particle will be moving backwards when velocity is negative. Now, if you look at your graph, you've got negative velocity. See here, when is velocity 0? We got those points. So this point on the graph here, we know that this is pi, that's pi on 2. We've just worked out that this is pi on 6 and that this point here, that's the time, is 5 pi on 6. So velocity is negative between, down here, from, so I might just put that over, I'm going to have to fit that somewhere else. Just a bit squashy down there. I'll just put it over the page. So you probably can't even see what I'm doing. So the velocity is negative between pi on 6 seconds and 5 pi on 6 seconds. I'll just put that over the page. So therefore, velocity is negative between, so from pi on 6 less than t, or when instead of from, you can put when, is less than 5 pi on 6 seconds. When. Okay, that's the end of question C. So in other words, particle moves backwards, particle moving backwards. That's what moving backwards means, velocity is negative. Okay, now part D. It says, what are the maximum and minimum velocities and where do they occur? I'm going to have to, we'll just go back to the diagram of the velocity. So your maximum velocity is here, it's 3, and it's 3 meters per second, and it's when, actually I'm going to resketch that. So I'm just going to do that here. Draw this velocity diagram again. And that's 3, and that's v. That's time, and you can't see what I'm doing. 2 pi, here is pi. Right, velocity is maximum up here. So the velocity is maximum when t equals here 3 pi on 2 seconds. And the maximum velocity is 3 meters per second. So maximum velocity 3 meters per second when time is 3 pi on 2 seconds. And if you look at the equation for displacement, when t equals 3 pi on 2, x is equal to 2 cos 3 pi on 2 plus 3 pi on 2. So this is the position of the particle, because it says what are the maximum and minimum velocities and when do they occur. We've got that and the maximum velocity and where, so that's the position. Cos of 3 pi on 2, that's cos of 270, that's just a cos curve, which is 0. So cos 3 pi on 2 is 0, so therefore it occurs at 3 pi on 2 meters to the right of the origin. Okay, so we get that when t is 3 pi on 2, we get x equals 3 pi on 2 meters. Now, for the minimum velocity, that's down here. So we've got the minimum velocity equals -1 meter per second, and that is when halfway between 0 and pi, which is pi on 2. It's when t equals pi on 2 and when x is 2 cos pi on 2 plus pi on 2. So just substituting into the formula for x. Now cos pi on 2 is 0 as well, so when x is pi on 2 meters as well. So it's when it's -1 meter per second when t is pi on 2 and the position is pi on 2 meters as well. Now for part E is to find the change in displacement. So change in displacement. It's different to distance travelled, very, very different. Change in displacement is final displacement minus initial displacement. Now, where is the particle originally? Now, we know that x equals 2 cos t plus t. So, when x is 0, no, when t is 0, sorry. So, when time is 0, where is the particle? X equals 2 cos 0 plus 0, which is 2. So the particle's at 2 meters, so that's initially, it's at 2. And the particle travels, we were told in the question, for 2 pi seconds. So when t equals 2 pi, x equals 2 cos 2 pi plus 0. Now cos of 2 pi is 1, so it's not plus 0, it's plus 2 pi. So therefore the position of the particle is cos of 2 pi is 1, so it's 2 plus 2 pi. So therefore the final displacement is 2 plus 2 pi minus the initial displacement of 2, which gives us a change in displacement of 2 pi meters. So therefore, now the average velocity is not distance travelled over time, it's displacement, change in displacement over time. And so the displacement is 2 pi, and the time is the period, which is also 2 pi. So it's 2 pi meters over 2 pi seconds. Therefore, the average velocity is 1 meter per second. And now for the last part of the question is to sketch the displacement time graph and hence find the distance travelled and the average speed. Now we know that the initial displacement was 2. So I'll just put that. I might put that down here somewhere. So initial displacement is 2. And we know that the final displacement at 2 pi seconds is 2 plus 2 pi. Now, if I have this fairly to scale, 2 plus 2 pi is 8.23. So I've got 2, 4, 6, 8. We'll say that this is 2 plus 2 pi. So I know 2 positions so far. That initially the particle, up there, initially the particle is 2 meters to the right of the origin. Okay, now I do have some other positions as well. If we look back, when time is pi on 6, I'm just putting these in, we know that the particle is at root 3, so I also know that when t is pi on 6, x is, this is from an earlier part, 3 plus pi on 6 meters, and when t is 5 pi on 6, x is 5 pi on 6 minus root 3 meters. Now that we can work out what those approximate values are, but we were also told that at these times velocity was 0, which means that the gradient of this displacement graph would be 0 because velocity is the gradient of the displacement graph. So 3 plus pi on 6 is 3 plus pi divided by 6 is approximately 3.5. And 5 pi divided by 6 is approximately 2.6. So you can sort of do this to some sort of scale. That would be 2.6 is about there. And 3.5 at pi on 6, if that's pi on 2, this would be pi on 4, pi on 6 would be somewhere here, 3, 2, this is 4, so that's a bit high. Because if that's 2 and that's 4, 3.5 is about here. And at 5 pi on 6, we've got about 2.6, it's here. Now we know that we've got stationary points. So these are stationary points at pi on 6, and time is pi on 6 and 5 pi on 6. We're just going to have to work out if they're maximum or minimum. Now what I'm going to do, we're going to be able to tell by the acceleration. So I've got the acceleration curve here. It's the acceleration curve up here. Now actually, I'm just going to move this screen. Here's the acceleration graph. I've actually got a velocity curve there as well. So let's see, between pi on 6 and 5 pi on 6, looking back at previous stuff, the velocity was negative, meaning that the gradient of the curve between pi on 6 and 5 pi on 6 is negative. So it's got to be looking like this. Now we know that we've got a stationary point at pi on 6, so it must be a maximum. And this must be a minimum, okay, at 5 pi on 6. And a maximum there. Okay, it's not the best graph in the world. Okay, now, and let's just look at this with acceleration if we've got concave up. So we do, this is the acceleration graph. Actually, no. This is acceleration positive from pi on 2. Yes. So here at pi on 2, we have an inflection. So it would look like this, and then an inflection. So concave up from pi on 2, and let's look here. Acceleration is negative from 0 to pi on 2, meaning concave down on the original graph. And we do have concave down on the original graph. So therefore, that stationary point at pi on 6, because v is 0 there, gradient there is like that. All right, I might just, this is really not the best graph that I've drawn here. I'll just try and make this look a bit more like a max, bring it down a bit, and then, yeah, bring that up a bit. And here's my inflection. Okay, sorry, I don't know if that's any better. Okay, and then let's just look at velocity. So velocity from that 5 pi and 6, the velocity is positive for the rest of it, so meaning positive gradient. And the steepest velocity here is at 3 pi and 2. We've got a maximum velocity. So we're still positive, and it'd be the steepest point of the graph here, and then it would taper off. Okay. All right, I would just get it going, like tapering off. Don't know what happens after that, okay? But this needs to be, now let's look at concavity as well. Here's the acceleration from 3 pi and 2. So from pi and 2 to 3 pi and 2, it's concave up because the acceleration values are positive. And from 3 pi and 2 onwards, it's concave down because the acceleration values are negative. So we need an inflection there at 3 pi and 2, and it's concave down. So the graph looks like that. Okay, so you've got a minimum down here, local minimum, a maximum. You've got an inflection at pi and 2. You've got an inflection at 3 pi and 2. And it stops there at 2 pi. So I'll just put some points on the graph. When t is 2 pi, x is 2 plus 2 pi. When t is 3 pi on 2, I don't think we've got that one. Don't think I've got that. Yes, I do. When t is 3 pi on 2, it's further up the page. X is also 3 pi on 2. Now, 3 pi on 2. So when t is 3 pi on 2, x is 3 pi on 2, which is approximately 4.7, and that makes sense, okay? So we've got that this value is, and I can just put it across here, that this is 3 pi on 2. Okay, this value here, 5 pi and 6, we've got 5 pi and 6 minus root 3. Don't know how I'm going to put that one, but you can just, you know, say that this is 5 pi on 6, 5 pi on 6 minus root 3. And do the same for this pi on 6 one, or just indicate that one here on the axis. That is, that's 3 plus pi on 6, this point here. Okay, and we can see that point there, and this one as well. When it's pi on 2, I believe that this is the point pi on 2 and pi on 2 as well. Because yes, we saw that in an earlier part when t is pi on 2, x is pi on 2, which is approximately 1.57. Okay, so pi divided by 2. Pi divided by 2, yes, is 1.57. So we've got all those points marked out on the graph. And you can just do them under each point if you want, or like that. Okay, so that's 2 pi, comma, etc. Okay, that's the end of that worksheet.